In this video, we're going to cover section 1.16, kinetic isotope effects. So far, we have considered reactions that are either one-step reactions or are multi-step reactions, in which the rate-determining step is known. In many cases, we may be able to propose a reasonable mechanism for a multi-step reaction, but we may not know which step is rate-determining. For example, let's consider the oxidation of a secondary alcohol by aqueous chromic acid. The mechanism involves two steps, where first we have our alcohol interacting with chromic acid in a fast and reversible manner to form the chromate ester. And then in a second subsequent step, the chromate ester undergoes reaction with water to form a ketone. So a central question about this reaction concerns the CH bond in the chromate ester. Does the rate-determining step occur before this bond is broken, perhaps during formation of the chromate ester? Is it the breaking of this bond? Or does it occur after this bond is broken? For example, through the decomposition of a carbanionic intermediate in which the oxygen-chromium bond is still intact. To answer these questions, we can use a kinetic method to determine changes in bonding during the rate-determining step. This method is the study of kinetic isotope effects, in which the rate of a reaction changes when an atom is replaced by a different, usually heavier, isotope. If there is a kinetic effect upon replacement of an atom to which a bond is broken, then we observe a primary kinetic isotope effect. If, however, the kinetic effect results from placing an isotope elsewhere in the reactant, then we observe a secondary kinetic isotope effect. So in the next two subsections, we're going to discuss both primary and secondary kinetic isotope effects and show you how these types of studies can be very useful in determining the rate-determining step of a complex reaction mechanism. So let's consider first a unimolecular thermal dissociation of a CH sigma bond. The electronic energy of the molecule varies as a function of the internuclear distance and can be described by a curve. So let's look at a diagram of this curve. So here we have the energy plotted against the internuclear separation. And again, we're looking at that carbon-hydrogen sigma bond. And so if we extend that bond, at some point that bond will break, and this is your dissociation limit. And if we try to compress that bond, at some point the repulsion between the nuclei will be too great. And here we have the internuclear separation of that CH bond at equilibrium, given by the symbol R subscript E. Now, superimposed on the electronic energy curve is a set of vibrational energy levels, epsilon equals 0, 1, 2, and so on. The energy of each vibrational level is given by this formula. So we have the energy is equal to h nu bracket epsilon plus 1/2, where nu is equal to 1 over 2 pi square root of k over mu, where k is the force constant for the molecular vibration, and mu is the reduced mass for the masses m1 and m2, that is the masses of, in this case, the carbon atom and the hydrogen atom. And so in our diagram, these are the vibrational levels. Okay, so this is the lowest vibrational level for a carbon deuterium bond, and this is the lowest vibrational level for a carbon hydrogen bond. At room temperature, 99% of molecules are in their 0th vibrational level, and the vibrational energy of the molecule is equal to 1/2 h nu. This energy is called the 0-point energy, and it's given the symbol E subscript 0. So the energy associated with the bond breaking is the difference in energy between the 0th vibrational energy level and the energy of the dissociative bond, which we refer to as the dissociation energy, which is denoted D subscript 0. So in our figure, this is the dissociation energy for a carbon-hydrogen bond, and this is the dissociation energy for a carbon-deuterium bond. And again, it is the difference between the respective vibrational level, the 0th vibrational level, and the dissociative limit. There is a difference, as shown in our diagram, between the dissociation energy for a CH bond in methane and that of a CD bond in a deuterated methane molecule. The substitution of one isotope for another does not alter the potential energy surface significantly. That is, the electronic structure, the binding forces remain the same. In fact, their energy should only differ in the vibrational and rotational energy levels associated with the CH and CD bonds. Due to the greater mass of deuterium, the 0-point energy is lower for a CD bond than a CH bond. As the reduced mass increases, nu decreases, so greater energy is required to break a CD bond than a CH bond. And we can see that if we go back to our expression for reduced mass, that as this value is going to increase, an increased value here is going to result in a lowering or a decrease in nu. And so that's going to place the 0-point energy for a CD bond as a lower energy than the 0-point energy of a CH bond. And that has the final effect of increasing the dissociation energy. So we require more energy to break a CD bond than we do to break a CH bond. And this is the primary focus of these kinetic isotope effects, is that we're looking at the differences in energy associated with the breaking of these CH and CD bonds. And if these bond breaking events are key to a rate determining step, then we expect to see a significant change in the rate for this reaction. Now we can calculate the difference in 0-point energy values for a CH and CD bond from the reduced masses and an estimate of the stretching force constant. Alternatively, we can determine the energy difference empirically through infrared spectroscopy. Recall, larger atoms give bonds that vibrate at lower frequencies, which correspond to a lower wave number of absorption. So for example, the 0-point energy for a CH stretching vibration that absorbs around 3,000 wave numbers can be calculated as follows. So the 0-point energy for that particular stretching frequency will be 1,500 wave numbers, 1/2 of that stretching vibration. Whereas the 0-point energy for a CD stretching vibration that absorbs around 2,200 wave numbers will be equal to 1,100 wave numbers. Again, 1/2 of that frequency. Therefore, the difference in the 0-point energies for the CH and CD bond in this example is equal to 400 wave numbers. And we can convert that to an energy using the conversion of 1 kilojoule per mole is equivalent to 83.593 wave numbers. And so we're left with about a 5 kilojoule per mole difference between the 0-point energy of a CD bond and a CH bond. Now, this dissociation energy difference means that the free energy of activation for the thermal dissociation reaction should be 4.78 kilojoules per mole greater for the CD dissociation than for the CH dissociation. The rate constants for the thermal CH dissociation, given as K subscript H, and for the thermal CD dissociation, given as K subscript D, are given by the following expressions. And we saw this earlier when we looked at parallel reactions, where the rate constant can be equated to this quotient multiplied by an exponential in which our exponent contains that free energy of activation. So these expressions show that the free energy or Gibbs energy of activation can be used to calculate the magnitude of the rate constant for the CH and CD bond. Now, if we want to compare the relative magnitude of these rate constants upon carrying out that substitution for the hydrogen atom for deuterium, we can take a ratio of these rate constants, which in effect is going to result in the subtraction of the exponents. So if we take the ratio, we have KH over KD. These two terms are going to cancel. And we're left with a subtraction of the exponents. So we have a minus delta G of activation for the CH bond over RT minus a minus, which is a plus, delta G double dagger for the CD bond over RT. And so our new exponent becomes a difference between those free energies or Gibbs energies of activation. So if we assume that the difference in the free energies of activation arises only from the difference in the 0 point energies of the stretching vibrations, then our final expression is we have a ratio of the rate constants is equal to a difference in the 0 point energies over RT. And so using the value that we just calculated previously, this 4.78 kilojoules per mole, if we now put this into our expression and divide the exponent by the gas constant and the temperature at which we're studying this particular example, we end up with an exponent of e to the 1.93. Again, we have two significant figures in the mantissa, so when we carry out the anti-logarithm of this particular value, we're going to have two sig figs in our final answer. So it turns out that our ratio KH over KD is going to be equal to 6.9. So what this tells us is for a purely unimolecular thermal reaction, the rate constant of a CH bond association should be approximately 7 times greater than that of a CD bond association. This difference is significant, and so this would imply that this particular CH-CD bond is a part of the rate determining step in this reaction mechanism. And one last point to make is that as we decrease the temperature at which we follow this particular reaction, we're going to observe an even greater isotope effect. So as this term gets lower, the exponential term will increase in value, and e to a larger number is going to result in a larger magnitude, i.e. ratio of KH to KD. So the observed range for primary isotope effects is large. For example, it can be as small as 1 and as great as 8, and rarely is it greater than that value. Now, the magnitude of the ratio of those two rate constants is a rough measure of the position of the transition state as described by the Hammond postulate. Based on the Hammond postulate, we can envision 3 scenarios for a reaction in which an atom A abstracts a hydrogen atom from a carbon atom. In an exothermic reaction, the transition state occurs early, to the left on a reaction coordinate diagram. In the second case, in the endothermic reaction, the transition state occurs late, to the right on a reaction coordinate diagram. And in a thermoneutral reaction, the transition state occurs near the center of a reaction coordinate diagram. The largest isotope effect is observed for the most symmetrical transition state, and we'll see that that is the thermoneutral reaction, whereas early or late transition states generally result in a much lower ratio, or KH over KD. In the first case, an exothermic reaction, the transition state closely resembles the reactant. If the transition state occurs early, then the CH or CD bond will be broken only slightly in the transition structure. So the stretching vibration in the transition state will be affected by the mass of the hydrogen or deuterium atom in much the same way as in the reactant. Therefore, the difference in the transition state energy for the CH or CD species will be nearly the same in the transition structure as in the reactant. In this scenario, the ratio of the rate constants for the CH or CD bond will be close to 1. So in the exothermic reaction, the transition state will occur early. And this means that the CH and CD bonds, because they're just starting to break, will be very similar to that of the reactants from which they came. And so when we compare the energy difference between the 0-point energy for the CD bond to that of the energy of the transition state for that same CD bond, this difference is almost equivalent to the difference for the CH bond. We don't see a significant difference. Because the relative change in the energy is similar, we don't expect to see a significant difference in the free energy of activation. That will mean the ratio of the rate constants will be close to 1. For the endothermic reaction, the transition state will closely resemble the product. So although the original CH or CD bond will be almost fully broken, the bond between hydrogen or deuterium and the acceptor molecule will be nearly fully developed. There will be almost the same difference in 0-point energies for the developing AH or AD bond in the transition structure as there was in the CH or CD bond in the reactant. Therefore, the free energy of activation for abstracting a deuterium will be very similar to that for abstracting a hydrogen atom. As a result, the ratio of the rate constants will be close to 1, as we saw for the exothermic reaction. So let's look at the figure for this particular scenario. So for the endothermic reaction, the transition structure is going to look very similar to the product state, which in this case is AH or AD. So at this particular point in time where we have our transition structure, the CH or CD bond has been fully broken, and the AH or AD bond is almost fully developed. And this is our late transition state. Our transition structure will resemble very closely what we observe for the product. Now, when we look at the 0-point energies of the reactant, again, we expect the 0-point energy of the CD bond to be lower than the CH bond due to the greater mass of deuterium compared with that of hydrogen. Similarly, when we look at the transition state structure, the transition state energy associated with the nearly developing AD bond lowers to the same extent when compared to the developing AH bond. And so overall, the difference in free energy associated with the CD to AD transition and the free energy associated with the CH to HA transition is going to be similar. So if these free energies are similar, then that results in the magnitude of those rate constants also being similar, which is why we see a ratio close to 1 for the endothermic reaction, similar to what we saw for the exothermic reaction. Now, in our third and last example is the thermoneutral reaction. In this reaction, the transition state is symmetrically located along the reaction coordinate. Now the hydrogen atom does not move in the vibrational mode, so the frequency of the vibration does not depend on its mass. As a result, the transition state energy associated with the CD bond is equal to the transition state energy associated with the CH bond. So these energies are the same whether it's a hydrogen or deuterium atom that is being abstracted. In this case, the free energy of activation for the abstraction of hydrogen and deuterium will differ by an amount equal to the difference in the CH and CD bond 0-point energies. As a result, there should be a significant kinetic isotope effect. As in the example we started this lecture with, the oxidation of a secondary alcohol by aqueous chromic acid has a kinetic isotope effect of approximately 6. This strongly suggests that the breaking of the CH bond is the rate determining step of this reaction. So let's look at the energy diagram for this thermoneutral reaction. So in the thermoneutral reaction, the transition state is symmetrically located between the reactant and product states. And the hydrogen or deuterium atom is also midway between the original carbon atom and the accepting atom. As a result, the hydrogen or deuterium atom, they're not vibrationally active, and therefore their frequencies are going to be the same because they don't depend on the mass of the atom. The hydrogen and deuterium atom are not moving. So as a result, the difference in the free energy of activation is going to be entirely dependent upon the 0-point energy of the CD and CH bond. And as we know, due to the greater mass of deuterium, it's going to have a lower 0-point energy. As a result, the free energy of activation for the deuterium system will be greater than the free energy of activation in the hydrogen system. As a result, we will observe a strong primary kinetic isotope effect because the ratio of the rate constants will be affected by this significant difference in free energy. So now let's look at secondary kinetic isotope effects. A secondary kinetic isotope effect can arise when a bond to the isotope is not broken during the rate determining step of a reaction. Generally, secondary kinetic isotope effects are much smaller in magnitude than our primary kinetic isotope effects. Nevertheless, secondary kinetic isotope effects can serve also as useful probes of transition state structure. Secondary kinetic isotope effects are often seen for hybridization changes of the type sp3 hybridized to sp2 hybridized or sp2 hybridized to sp hybridized. Let's consider the ionization of an alkyl halide. The carbon orbital involved in the CH bond changes from sp3 to sp2 upon formation of the carbocation. Such reactions are slower when the hydrogen bound to the alpha carbon is replaced with deuterium. This is due to the effect of the change in the hybridization on the energies of the CH and CD bending vibrations. A typical secondary hydrogen kinetic isotope effect has a ratio of approximately 1.15. So let's look at this example more closely as to where this secondary kinetic isotope effect arises from. So we have our alkyl halide, and this is the CH-CD bond that we're interested in. We're developing a partial positive charge on the carbon and a partial minus charge on the outgoing halide. Note that this carbon-hydrogen bond is not directly involved in the bond breaking event. It is secondary to that event. So if we look at the various frequencies associated with this CH bond and similarly the CD bond between the reactant state and the transition state, we can see that for the CH stretch, we see very little difference, only 100 wave numbers between the reactant and the transition state. For the CH bend in plane, that is this CH bond bending within the plane of the screen, again, we see no difference in the frequency for that particular motion. However, for the CH bend out of plane, where this carbon-hydrogen bond is going to bend towards you and away from you, we see a significant difference in the frequency for that particular vibration between the reactant and the transition state. So it's this difference in frequency that will be magnified when we replace the hydrogen with the deuterium atom. And so the CH bend and the CD bend, these out-of-plane bends, will vary significantly during the course of this reaction. And as a result, we will observe a secondary kinetic isotope effect of approximately 1.15. So if you have any questions about kinetic isotope effects, whether it be primary or secondary, by all means, send me an email. Thanks.